Chapter 2 is the second part of the first homework assignment. And so, Chapter 2 goes over different types of energy and the different types of matter. So, energy is the ability to do work. Energy uh, doesn't always have to be associated with actually doing the work, but anything that allows us to have that ability is classified as energy. And so we have two main types of energy. We have potential and kinetic. And if you think about the differences between the two, right? Potential, if something has potential, right, it's not actually doing it, it has the potential to do it. And so that's going to be the big difference here. And if you think about something like food, all right, food has gives us the ability to do work. The food doesn't actually do the work, but it's going to give us energy so that we ourselves can do the work. So potential energy is just stored energy. It has a potential to do something, and so it's going to store it, and it's going to be allowing it whatever we're talking about to do something later on. So it's going to give us that ability to do work at a later time. And so a couple of examples listed here is water behind a dam. So um, one major thing for potential energy is height. So anything that is higher above the ground has more potential to do work. So if you think about if we have two balls, one maybe on top of a desk and then one at the top of the ceiling, right? If we let go of those two balls to drop to the floor, that ball that's toward the ceiling is going to be able to reach a faster speed, right? It was higher above the ground. It's going to be able to fall for a longer time. And so that ball that's up at the ceiling has a higher potential energy. It has a higher ability to do work. Whereas the ball that was just on the desk, it was lower toward the ground. And so it doesn't have as much of an ability, it doesn't have as much stored energy. Another good example is a spring. And so we have different types of springs, and different springs have, I guess, more coils or less coils. They can there some springs are more springy, and so whichever ones that the different types of springs can have a different amount of potential energy. And then the ones that we'll pretty much be talking about in this class deal with chemical bonds. And so many chemicals have stored energy in those bonds. And when we break those bonds, we can release that energy because it's stored in those bonds. And so, like we said with the food example earlier, when we take in food, food has the ability to give us allow us to do work. And so that's because we're going to break those bonds and we make new bonds, and all of those reactions allow us to reach and obtain that energy for us to do work. Whereas kinetic energy is the energy associated with motion. Anything that's moving has kinetic energy. All right, so in that picture with the waterfall, right, the water that's falling, all right, it has kinetic energy. It had potential when it was just sitting still and it was up on the top of that dam, but when it actually starts to fall, it's transferring that potential energy into kinetic energy. When it starts moving, it's kinetic energy. Um, so anything that's associated with moving is associated with kinetic energy. And so here we'll just look at these different examples and different situations, and we need to identify which is potential and which is kinetic. So rollerblading in A, rollerblading, you're going to be moving. So anything that's moving, that's associated with kinetic energy. So A is going to be kinetic energy. A peanut butter and jelly sandwich, we said before, energy, food allows us to have the potential to do work. It gives us that ability. So we need to break down those bonds and form new bonds in our digestion. And so that gives us the ability to do work later on. And so that's stored energy. So B is stored energy or potential energy. C, mowing the lawn. So in mowing the lawn, we're going to have to be moving that lawn mower. And so anything with moving is kinetic energy. And then gasoline in the gas tank. So in this one, we're not actually burning the gas yet. It's just the gasoline sitting in the gas tank. And so that gasoline has the potential to do work. It has the potential to burn and the potential to break down those bonds. And so anything that has potential is potential energy. So heat is another type of energy we talk about in this class, and that's thermal energy. And it's thermal energy is very much closely related to kinetic energy because it's associated and related to the amount of motion of the particles. And so when we have particles moving faster, there's going to be more thermal energy associated with them. So you can kind of think about, if you're outside on a cold day and you want to heat your hands up, right? You're not going to rub your hands together very slowly. You're going to move them very fast, right? You want to move them. Your hands are going to have a lot of kinetic energy, and more kinetic energy results in more thermal energy. So, so there's a direct relationship there. So more kinetic energy and more thermal is equal to more thermal energy. We have two main units used for measuring the amount of energy or measuring heat. The more commonly accepted unit in science is joules. So you see joules a lot more often, but you do see calories. We see calories a lot in our everyday lives since we live in America. It's more universally accepted to use calories. And so we have this this ratio here, these conversion factors, that 4.184 joules is equal to 1 calorie. So we can use that, and if we ever need to do any type of conversion. As we went over in the metric system earlier, we'll sometimes see kilojoules. So kilojoules is equal to 1,000 joules. So kilojoules is bigger than a joule. And one, as we said, same thing here. 1 kilocalorie is equal to 1,000 calories. So it's review there in converting our prefixes in our metric system. So here you just see a scale of different scenarios and how much energy they have and how much energy they use and things like that. And so you can see on the bottom, it's the amount of energy used to sleep. And our body still needs to go through certain functions and processes in order for us to live. We need to breathe. Our brain is still active, and so we we do have energy there. And then the next one, we have energy from one serving of pasta. And so you can, if you were putting that together, you see that that takes 10 to the 6th joules, or 10 to the 3rd kilojoules. And if you were to calculate that out and calculate the amount of calories, you'd be like, that doesn't make any sense, because our diet is based on a 2,000 calorie diet. But just to warn you that the dietary calories are actually equivalent to kilocalories in our in terms of heat energy and thermal energy. So it's a little confusing in that respect. But you can see, if you go up the scale, the largest source of energy from in our solar system, the sun, and how much energy that gives us per second, and that's pretty high number there. So here we'll just do practice some conversions. So it's asked us how many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized. So In the same steps that we did earlier, we need to look at what the question is giving us and what we're trying to get, and try to figure out what conversion factor is going to allow us to get to what we are looking for. So we can just move on to the next slide and kind of show what to do here. So it says that we are given 150 joules. We need to get the calories. So our plan is to convert joules to calories. So we need to go back and you can look at the previous slides or look in your book and find that conversion factor. And so we saw, if you remember, 1 calorie is equal to 4.184 joules. So we have since we're trying to go from joules to calories, we want the joules to cancel out. So we want to have calories on top and joules on the bottom. And so we multiply 150 joules by 1 calorie over 4.184 joules, and we get 36 calories. And so since our number of 150 joules only has 2 significant figures, and that's the lowest number of significant figures, then we can only report 2 significant figures, which is 36. So when you think of heat and thermal energy, you typically think of temperature, and so we need to discuss the scales of different units of temperature. And so the 3 units of temperature is Fahrenheit, Celsius, and Kelvin. And in science, we typically use Celsius or Kelvin, and so we typically do not use the Fahrenheit scale. And so we'll talk about how we can convert between the different units. Interestingly enough, the Celsius scale is pretty much based on the properties of water. All right, if we all pretty much know that water freezes at 32 degrees Fahrenheit, but in the Celsius scale, it freezes at 0. And in the Fahrenheit scale, it boils at 212 degrees Fahrenheit, but it boils at 100 degrees Celsius. So like much of the other metric units, they're all based on powers of 10. And so that's what's nice and convenient about the Celsius scale. Is pretty easy to remember the degrees Celsius that water freezes and boils. So in this table is just a comparison of temperatures in the 3 different scales of different scenarios. One thing you can see is the bottom one, absolute 0. So absolute 0 is the coldest temperature that is possible in our universe, and that's what Kelvin is based off of. The unit Kelvin is based off of absolute 0, and at 0 Kelvin, that is absolute 0. That's nothing can get colder than that, and that's pretty much when everything stops moving. There's absolutely no thermal energy, and even things as small as electrons stop moving. So there's absolutely no thermal energy. Nothing can move at absolute 0. So here, what is the temperature of freezing water? And if you look back at the previous slide, right? Water freezes at 0 degrees Celsius. So you want to remember that. That won't always be given to you, so you want to remember that number. What is the temperature of boiling water? So it boiled at 212 degrees Fahrenheit. So A and B cannot be correct. 100 degrees Celsius and 373 Kelvin. And in a few slides, we'll talk about how we can convert between these different units. And so how do we actually get Kelvin from Celsius and different properties like that. And then the last one, how many Celsius units are between the boiling and freezing points of water? So it's just asking us, how many degrees between the boiling and freezing point of water. So water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So that's 100 different units. And so there you see the answers from those questions. All right, so I don't really like to use Fahrenheit too much. There won't be too much of this really in on a test or anything, but I think it's a something worthwhile to go over because uh, in the medical fields in America, we a lot of times do use Fahrenheit, so we will have to discuss this a bit. So to go from Fahrenheit to Celsius, um, we use this ratio that um, this 9/5 ratio that you see here, or the 1.8 degrees Fahrenheit per degree Celsius. And then we also have to add 32 degrees to the Celsius scale to convert to Fahrenheit. So the final equation comes to the degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. And I'm not going to ask you to memorize that equation. If we need to use that any time on a quiz or a test, I will provide that to you. Um, Similarly, if we need to go in the opposite direction, so since we just solved the equation to go from Celsius to Fahrenheit, here we can just move our equation around to go from uh, Fahrenheit to Celsius. And so just by looking here, I'm not going to ask you to solve this at any time. And again, but you'll have to on a quiz or a test, I may just give you the one equation, and so you wouldn't have to rearrange it or just plug all the other numbers in to solve for the degrees Celsius. So here we see that the equation becomes the degrees Celsius is equal to the Fahrenheit minus 32 all over the 1.8. And as I mentioned before, the coldest possible temperature is absolute zero. And so that is negative 273.15 degrees Celsius. Or another way to say that is 0 Kelvin. So the when you move 1 degree Celsius, you also move 1 degree Kelvin. So um, their differences between the two scales are the same. The only thing you need to do to convert between the two different units is to add 273 to degrees Celsius to get to Kelvin, or in the opposite direction, you subtract 273 from the Kelvin to go solve for the Celsius. All right, and so if you were to look at this chart again and you were to use your equations and go from one column to another, you just would see that it worked out perfectly. So that's why we see here water freezes 0 degrees Celsius. If you remember, we go from Celsius to Kelvin, we have to add 273. So that's why it's equal to 273. Just in the opposite direction, Kelvin to Celsius. All right, we only have to do subtract 273. So 273 minus 273 is equal to 0. So 0 degrees Celsius. And you can see the same things at absolute 0. All right, and so that's where we get these properties in looking at water. You can see that, as I said before, the differences between the Kelvin units is the same as the differences in Celsius units. So there's water freezes at 273 Kelvin and boils at 373 Kelvin. So there's 100 different units there. All right, difference of 100. Same thing with the Celsius. All right, 0 degrees Celsius and 100 degrees Celsius is a difference of 100. Relating this to health, our normal body temperatures we mostly have learned is body temperature is 98.6 degrees Celsius Fahrenheit, and which is equivalent to 37 degrees Celsius. But our temperature does fluctuate throughout the day, and so we may have slightly lower in the morning and slightly higher in the evening. But on average, the normal is 98.6 or at 37 degrees Celsius. um, So, just like before, in all our other problems, when we were trying to solve for some property, we need to look at and state what we are given and state what we are needing to go solve for. And so then we can write the equation and rearrange it in any way that we may need to. And then we just put in our values and we can calculate our value. And in this case, it's all going to be temperatures. So here, if we have a person with hypothermia, and so they're going to be colder than average temperature. If they are at 34.8 degrees Celsius, what is their temperature in Fahrenheit? So you won't have to memorize the equation. You can just have that equation written down, and we know that we were given Celsius. It says that we need to go to Fahrenheit. So we want to have Fahrenheit by itself, and so the Fahrenheit equal to 1.8 times the degrees Celsius plus 32. So then we can just plug in our values and we solve for it and we get 94.6. And one thing you can note here is that 1.8 and that 32, those are exact numbers. So we do not get any significant figure information from those values. So the only source of significant figures is from the numbers or the values that were given to us, which is the 34.8. Here, we'll do another one. So it says a pepperoni pizza is baked at 455 degrees Fahrenheit. What is the temperature needed on the Celsius scale? So we need to go from Fahrenheit to Celsius. All right, so we're given Fahrenheit. We need to go to Celsius. So we're not going to use the equation that we used in the previous equation or question. We're going to use the opposite. All right, so we're going to use that the degrees Celsius is equal to Fahrenheit minus 32 over 1.8. And so from there we need to plug in our values. We have the 455 degrees Fahrenheit, and it's the only thing we really need to plug in, and we get 235 degrees Celsius. And so we have three significant, since we're doing the subtraction, the only source of significant figures is that 455, and it's in the ones place, and that's where we finish our value. All right. On a cold winter day, the temperature is minus 15 degrees Celsius. What is the temperature in Fahrenheit? So here we're going to use much like the first one we did together. And so we are given Celsius, and we need to go to Fahrenheit. And so we use the Fahrenheit is equal to 1.8 degrees Celsius plus 32. And so when we plug our Celsius in, we have a 1.8 times the negative 15 plus 32. And that brings us to 5 degrees Fahrenheit. All right, just make sure that you you use the negative sign properly in your equation. All right, so now in this question, we're asked what's the normal body temperature of 37 degrees Celsius in Kelvin, and without having to look at the table that was given to us. And so here we are given Celsius, we need to get to Kelvin. And the equation that's given to us is Kelvin is equal to Celsius plus 273. So all we will need to do is add 273 to our degrees Celsius. And when we do that, we get 310. And since we're doing an adding problem, then our significant figures end in the ones place. So the chapter is energy and matter. We talked a bit about energy, and now we'll get to matter. And matter is just anything that has mass and occupies space. So it's anything as small as an electron or any type of subatomic particle to things that we can see every day, like our water, wood, big as planets and stars and whatever you can see. And so There's two main types of matter. We have either mixtures or pure substances, and we'll talk about the differences between those and some subsections of those. So a pure substance can have a fixed or a constant composition. So it's going to be the same every time, no matter what. It's pure. And a pure substance can either be found as an element or a compound. So we'll talk about elements and what is an element and the different types of elements later on in the course. And then we can put these elements together and these different types of atoms together to form compounds. And so that compound is just something that has two or more elements together, combined, usually through some bonds. And so pure substances are pure. They are found the same every time. You're not going to find them different in any way. And we can have elements, one particular type of atom. It's going to be pure. It's just that one atom and only that one atom, or a compound where we can put these couple different atoms or a few different atoms together to form a compound, but that compound is the same every time you see it. Elements are pure substances that contain only one type of atom. And so an elements are, if you ever heard of the periodic table, that's a whole chart of different types of elements. Well, in this example here, they give us copper. All right, so copper is a type of element. Lead is a type of element. Aluminum is a type of element. Those are just some metals. Some non-metal examples: oxygen, neon. So there's many different types of elements, and we'll talk about the properties of these elements and what makes them different from a chemical standpoint later on in the course. When we have compounds, compounds contain two or more of these different elements and combined in a definite ratio. So that just means you're going to have a certain number of these elements, and they're going to have a particular number of each of these elements. All right, so one common compound that you probably have heard, H2O. H2O has two H's and one O every time you see it. So water is a pure compound. It's always going to have those two H's or two hydrogens and one oxygen, and it's always found that way. Salt, like table salt, it always has just one Na or one sodium and one Cl or one chlorine. That's it, and it's going to be found that way every time in nature. So here, as our example was table salt or sodium chloride is made up of sodium and chlorine, and compounds are interesting because the elements by themselves can have much different properties than when they are combined in a compound. So sodium is a metal, and like metals, they are shiny and they're usually silver in color, not all the time, but usually. And so you see that picture of sodium there. We have very close bonds together, and it's just sodium. And then chlorine is actually a gas, and you see it's a yellowish gas there. And when you combine them together, you get something totally different. You get this white crystalline substance that we know as salt. And it has totally different physical properties, has totally different chemical properties than the elements by themselves. So those were pure substances. Now we'll talk about mixtures. So a mixture, when you have a mixture of something, they have a mixture of different things. They're going to have more than just one substance, and they're mixed together physically, not chemically. So you can have many different types of mixtures, but they're going to be not chemically bonded together. It's their composition is not constant. You can find different ratios of the different parts. You know, you may have, if we make something like a mixture of sugar water, right? You have sugar and you have water. They're not. You're still gonna have, even though you add the sugar in there and it dissolves, it's still a mixture of just sugar and just water, and they don't chemically react to each other. They um, you can have different amounts of sugar, you can have different amounts of water, and so that composition is not the same. And with these mixtures, we can separate them through physical methods. So if we were had this sugar water and we wanted to separate the sugar from the water, we could just heat it up. And if we heat it up, then we can separate the water. The water will evaporate and the sugar will be left in our container. And so they can just be separated through these physical methods. So a physical separation just involves physical changes. So like we said before, we can boil something off, we can separate it through something like a strainer or a filter, and so these are just physical separations. And that's what makes mixtures unique, is that you can do that just through physical methods. We mentioned filtration, and filtration, is just much like a strainer, just usually much smaller scale. We also have things like chromatography, and there's many different types of chromatography. In the picture here, we see what we call a TLC, a thin layer chromatography, and our paper chromatography. And what's happening there is that those chemicals are moving up that paper, and they are separating out. Some are able to move faster or further up than others, and you'll find different chemicals at different heights of that on that paper. And so mixtures can be either homogeneous or heterogeneous. So homo is a prefix meaning the same, and hetero means different. And so when we have a homogeneous mixture, they are uniform. It's going to be constant throughout. So you'll find the same amount of each of the substances no matter where you are in the mixture. But if we have a heterogeneous mixture, that means that we can find different amounts of these different substances in our total mixture. So as we said before, homogeneous, homo means the same, so it's going to be the same throughout. So in a homogeneous mixture, you're going to find the same ratio of your elements or your compounds throughout that mixture. And so here we have brass. Brass is a mixture of copper and zinc. They're not a compound because the copper and zinc are not reacting with each other. All right, but we have this mixture that makes the brass, and it's homogeneous because it's constant throughout. No matter where you look at the elements and the atoms on that vase, then you're going to find the same ratio of copper and zinc atoms. Now you can look on the bottom, you can look on the top, you can look on the sides. No matter what, if you could, visually look at each atom, you'll find the same ratio of copper and zinc atom. Whereas heterogeneous is not uniform. It's not going to be the same throughout. All right, and so here we see a mixture of water and copper. Put some pennies in a cup of water. It is technically a mixture. Again, they're not reacting with each other, so that's why it's a mixture. And so here we'll find different amounts of copper and different amounts of water at different places in this cup. Right? We'll find all the copper on the bottom. We're not going to find the copper at the top of our glass, we're not going to find at least the same amount of copper in our glass. And so that's why it's heterogeneous. It's not constant throughout. So at different places in this mixture, you'll find different amounts of water and different amounts of copper. All right, and so this is a nice flow chart to figure out what the pieces of matter are classified as. And so this may be a useful flow chart to use in your homeworks. So here we need to identify the different these different substances as either being a pure substance or a mixture. And so here in A we have pasta and tomato sauce, one of my favorites. And here, if we have pasta and tomato sauce, it's going to be, we're not dealing with, the pasta is not going to be reacting and combining with the tomato sauce. So it cannot be a pure substance. So it's going to have to be some type of mixture. And at different points, if we have a bowl of pasta, we may find a section of that bowl that has more tomato sauce, other portions that may have more pasta, and so it's not going to be constant throughout. And so in that case, it's going to be a heterogeneous mixture. Aluminum foil. Aluminum foil is made from aluminum. It's a it's an element. So if you look on the periodic table, you'll find aluminum on that periodic table. So it's a particular type of element, and so that's the type of matter it is. Helium, again, is very much the same. It's found on the periodic table. It's a particular type of element, so it's a pure substance or an element. And then air. Air is going to be, we have in our air, we have oxygen, we have nitrogen, we have carbon dioxide, argon, and all these other different things in air. So air is classified as a mixture. All right, and there you see. And here we're asked to classify them as a homogeneous or heterogeneous mixture. So a hot fudge sundae. So if you think about our fudge is not going to chemically react and combine with our ice cream. It's just physically mixed in, and so that's going to be that's why it's a mixture. And if we have a bowl of a hot fudge sundae, we'll find different amounts of fudge or different amounts of ice cream in different parts of that bowl. So it's going to be classified as a heterogeneous mixture. If we have a clear shampoo, if we'll have many different compounds in there, and hopefully it would be a homogeneous mixture, the constant throughout. Hopefully, the bottle of shampoo is just as good in the beginning as it is toward the end or the bottom of that bottle, and so it is going to be a homogeneous mixture. Sugar water. When you mix in sugar and water, the sugar is going to dissolve and mix throughout the water, and so it's going to be a homogeneous mixture. If something can dissolve and mix within the solution, then it should be a homogeneous mixture. All right, and so no matter where you take a sample of your sugar water in your container, it should contain the same amount of sugar and water throughout. You kind of think about if you have sweet tea. Basically, sweet tea is just sugar water with some tea added in it, and hopefully it's going to be just as sweet on the top or the beginning of your container or compared to the end or the bottom. And lastly is peach pie. Peach pie, we have different parts of the pie. We have our crust, we have the peaches and the syrup and all that kind of stuff. So it's not going to be the same throughout. So if it's different, it's got to be heterogeneous mixture. All right, and there you see. Now we'll talk about different types of matter as far as their physical states. So we'll start with solids. All right, so solids is defined as something that has definite shape and definite volume. So definite shape just means that it has a shape that is going to have some type of definition. It's going to, if you put it on a desk or a bench, that shape is not going to change. It's going to keep that shape. It's definite. It has its own shape. It doesn't take the shape of a container. If you put a rock in a container, that rock isn't going to change its shape to fit that container. It's just going to stay the same shape it has. A definite, and it also has a definite volume. So definite volume, it means that that volume is not going to change. It's going to remain constant. If you have, you know, a cubic meter of sand, that's a volume. It's not going to change get in different conditions. If it's under high pressure or low pressure or whatever you have or different temperatures, it's going to remain that same volume. In a solid, the particles are close together, and so we have if it contains if the atoms are going to be very close together, the molecules are very close together, and they're in a rigid pattern. So that just means that they're in place. They're not going to move around. All right, so that pattern that those atoms and molecules are in are going to stay that way, and the particles vibrate. All right, so all matter has some type of movement to it. Solids have the least movement. All right, they are move very, very slowly, but there is some vibration to it. Where we compare liquids, liquids have a definite volume, but do not have a definite shape. So what that means is that um, if we have like that water that's being poured in that glass, that water had a certain shape to it in the bottle, and it took the shape of the bottle. But when we transfer it to the cup, it does not stay the same shape as the bottle. It's going to take the shape of a cup. So it does not have a definite shape, but it does have a definite volume. So that just means that the volume is not going to change. If we buy a gallon of milk, it comes in that milk container. We can put it in a different jug. We can put it in a bucket, but it's still going to have just a gallon of milk. All right, so it has a definite volume. It's not going to change. The particles in liquids are close together, but they are, fluidic. They do move around. They are mobile, but these particles move. Still, they move pretty slow in random directions, but they are going to move a bit faster than solids and have more movement than solids. All right, but they're not going to be, and again, they're not going to be as close together as they are in solids. So, when we can't put our hand through, a desk because those particles are too close together. But when we talk about liquids, we can't put our hand through there because they're not as close together. And then lastly, we have gases. Gases do not have definite shape or definite volume. So don't have a definite shape because the gases will take the shape to wherever the gas is. If it's in the balloon, it'll take the shape of a balloon. If we have a different shaped balloon, it'll take the shape of that particular type of balloon. So it does not have a definite shape. And it does not have a definite volume. All right, we can change the amount of the volume of air by changing temperature or changing pressure, right? You're probably familiar with when you heat something up, it expands, in terms of gases. So if you leave a ball outside on a hot day, that ball will seem like it has more gas, but all it is that gas is expanded. And so it feels more firm. If you leave it outside on a cold day, it feels flat. It didn't necessarily lose air, just that gas has contracted and has gotten close together. So it does not have a definite volume. It can change given different pressures and temperatures. In gases, the particles are very far apart, right? If we were, an example of moving our hand through the different types of matter, when we move it through liquids, we have some resistance because they are somewhat close together. But in gases, we have no problem, like air, right? Air, we have free movement of our hands through the air because the particles are so far apart. And in gases, these particles are moving extremely fast. They have very little attraction to each other. There's a lot of kinetic energy associated with gases because they are moving so fast. All right, and so here's a nice comparison table of comparing the solids and the liquids and their different properties and characteristics. And so this would be a good thing to know. And so here we're just give these different characteristics and we'll classify them as either being solid, liquid, or gas. So if something has a definite volume but takes the shape of the container, all right? So when it says takes the shape of the container, I mean it does not have a definite shape. So that means it's going to be a liquid. Its particles are moving very rapidly. So if it's moving very fast, those have to be gases. If it fills the volume of a container, fills the volume of the container. So um, that is going to be a gas. A gas is going to take whatever shape it has of the container and it's going to fill it up. It's not going to just hang out just on the bottom and leave nothing on the top. It's going to fill up the whole thing. It has particles in a fixed arrangement, and that will be a solid. They're very rigid. That's just saying it's a rigid structure, and it has particles that are close together and are mobile. And so that one is going to be liquids. Liquids are still close together, but they still are fluidic. They still can move around a little bit, and so that would be liquid. So we just got done describing the physical states of matter, and now we can go into descriptions of other properties of matter. We'll begin with physical properties. And so physical properties are just properties that we can see or we can measure without changing the identity of the substance that we have. And so in here we can talk about, what shape does it have, what physical state, like solid, liquid, gas. Um, what are some of its properties, like when does it boil or freeze? When does it become a solid or a liquid or a gas? At what temperatures? How dense is it? What color is it? So, what if is it shiny? Is it does it have any luster or anything like that? So anything that you can see and some physical properties like the changing of their physical states and their physical states themselves. So, for example, this amount of copper, we can say its color is orange slash red. It's got an orangey red color to it. It does not have any particular type of odor to it. We can measure its melting or boiling point, and um, those are properties that we're still not changing the material itself. We're just changing it from a solid to a liquid, and we're just changing it from a liquid to a gas. So we're not, when we're melting it and boiling it, we're not changing what it's made of. We can say what it is at room temperature. We can say if it's shiny or not, the luster, if it conducts electricity or not, if it conducts heat or not. So all of those are um, uh, physical properties. We're not changing the actual um, uh, chemistry to it. We're not changing what it actually is and what it's made of. So often we have physical changes of substances, and so a physical change of a substance can be classified as a change in the state, uh, change in the physical shape. So a change in state is just, if we change from solid, liquid, or gas. Change in physical shape is if we can mold it in any type of way. If something melts, it's going to change shape, things like that. But the key thing is here is that we do not change the identity or composition of a substance. So, a physical property that we discussed was color. So even though color is a physical property, when something changes color, it's not necessarily a physical change, because usually when we change color, that means something has happened, a chemical change. Um, so you have to be careful in how you're going to, you know, determine if it's a physical change or not, or if it's chemical change or not. So the key thing here is that you're not changing the identity or composition of the substance. You're not changing, what it is made of. Copper is going to be made of just copper. So if copper changes color, right, then something has happened to it. Something has changed. If the copper turns blue, then it's something other than copper then. So even though it's a change in physical properties, doesn't necessarily mean it's a physical change, because it probably has changed the identity. So here, the example is water. Water can be found solid, liquid, or gas. We have ice, we have liquid water, we have steam. And so uh, you can ask yourself a question in terms of energy here, and it says, is water added or released when liquid water freezes? So when you are freezing water, do you have to add heat or take away heat? And so the answer should be you are going to be taking away heat. You need to remove that heat away from the water in order for it to become a solid. So the changing of state, we have melting and freezing points. So they are the same temperatures. They're just, in opposite directions. Melting, you are going from solid to liquid, and freezing, you're going from liquid to solid. So they're at the same temperatures. You're just going in opposite directions. All right. Same thing with evaporation and condensation. So they are at the same temperature. It's going to be the boiling point no matter what. That it's or in the condensation point, it's going to be at the same point, same temperature. They're just going opposite directions. So boiling or evaporation is going from liquid to gas, whereas condensation is going from gas to liquid. And so if you're going from gas to liquid, you're going to be taking away heat. If you're trying to go from liquid to gas, so you got to heat it up. If you want something to boil, you're going to have to add heat to it. We have these things called heating curves. And so a heating curve is just a chart of the amount of heat that you have to add, and the temperature that you are at, and usually indicates what physical state you are in. And so at the lowest temperatures and the lowest amount of heat, you're going to be at a state of solid. And so you have to add heat, and you have to have to increase temperature in order for that solid to heat up. And eventually that solid, if it heats up to the melting point, at that point it's going to start melting. And so an interesting fact here is that when it is melting, you are transitioning from solid and liquid, so they're both going to be present. And at that point, you still have to add heat, but the temperature will not change. It will not change until everything has converted to the liquid state. So once all the solid has transitioned to liquid, then the liquid can then again rise in temperature with the increase in heat. So it goes up and up and up and up and up during the heating process until it reaches the boiling point. And so very similarly, when we are at the boiling point, we have a mixture between liquid and gas, and we need to continue adding heat until all of that liquid boils to the physical state of gas. And so we are going to add heat, but the temperature does not increase until everything has transitioned from liquid to gas state. And so when we have all gas, then we can increase temperature again. And so we can just go up and up and up. All right, so the key thing there is when we are transitioning, when we're at those boiling and melting points, when we're at those transition points, we are not changing temperature until we have all reached that one physical state. All right, the same thing can be said in this cooling curve. It's the same thing, just in opposite directions. So if we're looking just at water, we start off with steam at the highest temperature and the most amount of heat. Then when we remove heat, it's going to cool down until it reaches the condensation point. And so in that case, we're transitioning from steam to water, from gas to liquid. And at that point, we are going to keep on removing heat, but our temperature does not fall until everything has converted to water, liquid water. Then when we do that, it can then uh, fall in temperature. And as you continue to remove heat, then you reach the freezing point. You have solid ice and liquid water together. And then when you have all ice, then as you continue to remove heat, then you can decrease in temperature again. A couple of transitions you may not have heard of is sublimation and deposition. Sublimation is when you go from solid to gas directly, so there's no middle ground of liquid. And then the opposite is deposition, going from gas to solid directly. And so there are just physical changes like before. One common example is dry ice. Dry ice, is just solid carbon dioxide. And when you have solid carbon dioxide and you have to keep it at a very cold temperature to keep it as a solid, and if you let it sit out, it's going to sublime. It's going to go directly from the solid to the gas. It's not going to melt into the liquid state at all. All right, so here we have the examples of the physical changes. We can have change of state, as in, going from all those physical changes, like melting and freezing and subliming and so on and so forth. Then we can have change in appearance, so we can have dissolving like the sugar in the water. We can have change in shape, so we can hammer it out. We can put it in, make it into wire, and mold it into whatever shape we want. Then we can have change in size. We can cut it up, we can grind it, we can sand it, things like that. But we're not changing the chemical composition. We're not changing what it's made of. And that's the key difference between chemical properties and chemical changes. So chemical property is the ability of a substance to change into a new substance. So how can it react? How can it make new materials? And when we have that chemical change, you're going to have something new. You're going to have a new composition, a new chemical makeup. And so with this new makeup, you will have new chemical and physical properties. You will have a new compound. And so it will not have the same properties as it did before, kind of like when we looked at salt. All right, we had sodium metal, and that had certain chemical and physical properties of being sodium. All right, it was shiny and it looked silvery and so on and so forth. And then we had the chlorine gas. It was a gas. It was yellow and toxic. But then when we combine those into NaCl or table salt, it's completely different. It is white, it is crystalline, it has a certain different taste to it, and it doesn't have the odor of the chlorine, and so there was something totally different. So when we have new chemical compositions, they have new properties. An example here is nails. If we have iron nails, right? Anything that's iron has the ability to rust. And so all rusting is going to be oxidized by oxygen. So the iron reacts with the oxygen to form this new compound called iron oxide. And iron oxide has that rusty color to it. It's not going to be that shiny silvery color anymore. And so that is a change in the physical property of the color because there's a chemical change going on. And so some examples is, even when silver tarnishes, it gets that black color to it. If we burn wood, all right, we form that flame. We're going to produce heat. It releases heat. You have the reaction of combustion, so you're going to release carbon dioxide and water vapor into the air. All those are good examples of chemical changes, and you have a change in chemical composition, and you're going to have a change in many of the other properties, physical and chemical properties. And so here's a table that has a nice little summary of the physical and chemical properties and changes. So it's just a nice little thing that you may want to be able to use in your homeworks and maybe study the differences between those. So here, let's just go through these and try to classify each as a physical or chemical change. So when we burn a candle, all right, we have that wick on fire. And so anything that's going to be on fire is going to go through combustion, and combustion is going to be a chemical change. We are going to, it's a specific type of reaction that when you burn something, you're going to react it with oxygen, and it's going to produce carbon dioxide and water. And so anything that burns is going to be a chemical change. Because you're going to be changing the chemical composition. And B, ice melting on the street. All right, if ice melts, it's going from solid to liquid. That's just a change in a physical state, and that is just a physical change. It's still going to be made up of H2O. It's still water, and so it's just a physical change. C, toasting a marshmallow. So there you are adding fire to it. You're going to, in the table before, it said caramelizing any type of sugar is a chemical change, and same thing here. You're going to change it so that sugar is going to be burnt. It turns different color because of that chemical change. And so C is going to be 2, chemical change. D, cutting a pizza. If you cut it up, you're still going to have pizza. It's still going to be made of cheese and tomato sauce and crust and everything like that. And so you're just making it and changing size. So that's just a physical change. And polishing a silver bowl. There you're removing the tarnish. You're protecting it and adding a protective layer on it. And so there should be a chemical change. All right, and so here you see the answers that we have just discussed, and so this brings us to the end of chapter 2, and so this should also bring us to the end of the information and that's required to complete the first homework assignment. And the first homework assignment is going to be due January 26th at the beginning of our lab meeting on that Monday. So make sure that it's done by the beginning of the lab period. If it's turned in any time during or after the lab period, it is considered late, and there's that late penalty. So you don't want to be subject to that. So I will post a video of work through problems, and you can see how I work through problems. And then if you have any questions, you can ask me during the lab meetings, and you can ask me through the email. Sometimes it's hard through the email, because you can't really show work for any calculations. It's pretty difficult to do so, but I'll do my best in explaining it. And so then on that January 26th, we'll also have our first quiz. So be prepared for that. And so again, the quiz should be very much aligned to the homework questions. So make sure you study and do your homework, as that will probably result in a good grade for your quiz as well. Okay, so Um, Thank you for listening.